Hello everyone and welcome to this video. In finite element analysis, boundary conditions are a critical part that can make or break our results. What makes boundary conditions so special? We know that there are different sources of variability in our analysis. For example, we have geometry, material property, loads, etc. Let's say that in a simulation, the load we apply on a system deviates by 5%. Then we know that the resulting stress or deformation too will be off by 5% in a linear analysis. However, for boundary conditions, it's another story. If an inappropriate boundary condition is used, the simulation may be far from correct. In many cases, the choice of boundary conditions can entirely change the nature of the problem we're solving. Hence, it is important to give proper thought to the choice of the supports for the model. Given a simulation problem to solve, determining which support to use can be the very first step in our thinking process. This video will help you to understand the different support types so that you can determine which support to use for different situations. Now, let's get started. So let us see what is a support. Supports help to truncate the domain. Suppose we want to model a vehicle's engine block, and we do not plan to have the roads, tires, and many other parts attached to the engine to be modeled. Truncating the model helps in efficiently obtaining numerical and accurate results without modeling other parts of the geometry that are not of primary interest. Thus, supports help to model the parts that are not present in the model but are interacting with it. For this engine block example, we can model only the engine block that is highlighted, but we also need to include the effect of the rest of the part through the use of supports or boundary conditions. Let us now investigate the different support types available in Ansys Mechanical and their meaning. The first one is a fixed support. All degree of freedoms are fixed or constrained for the scoped locations when this support type is used. For surface or line body, the rotations will be constrained as well. But one should be aware of the possibility of over-constraint because the nodes on fixed face cannot move at all. Let's look at a simple block with a fixed support on one end and a pressure load on the opposite side. Since the fixed support prevents any motion, we'll end up with a bulging of the material at the sides, as shown here, which may or may not be what you want. Now let's move to the next support type, the displacement support. A displacement support allows us to specify a zero or non-zero value to any three orthogonal directions. This support type can be used to model very common scenarios like displacement control testing of materials, such as tensile or compression test. Here we can see a tensile testing of a metallic specimen where one rigid jaw is fixed and the other rigid jaw is pulling it. Using supports, we can model this scenario of tensile test without modeling the jaws. In the simulation, we can apply a fixed support at one end, which models the fixed rigid jaw, and a displacement support at the other end, which models the rigid jaw pulling the specimen. Let's move on to the next support, the frictionless support. This support only constrains translational movement in the direction normal to the surface. For example, let's say that we have a similar block as shown earlier, this time with a frictionless support on one side and a pressure on the opposite face. Looking at this animation, we see that when the block is compressed, the face grows, which indicates the frictionless support does not restrict the in-plane motion. If using fixed support, the shape of the face would have remained the same. Same phenomenon can be seen when we pull the block. The face with the frictionless support will shrink in size since it is free to contract in plane. Next, we discuss the cylindrical support. This support is specific to cylindrical surfaces and constrains actual radial and/or tangential directions. This support can be thought of as a rigid pin fitting snugly inside of a cylindrical surface of our part of interest. We specify whether or not the nodes of the cylindrical surface can move freely in these three directions. A simple practical application of this support is for machinery with a rigid shaft. You can apply a cylindrical support on the hull of the machinery. If the shaft is free only to rotate, then the tangential motion of the cylindrical support can be set to free, and the radial and axial motion can be said to be fixed. However, we should be careful to only use the cylindrical support in small deflection analysis. Never use them in large deflection analysis. The reason for this is that the nodes of an element have Cartesian behavior. Suppose we have a cylinder, and the nodes can move only in x and y directions as indicated. It might happen that we constrain only x and not y, and when large deflection happens, y moves in tangential direction, not circumferential direction. So motion will continue to move tangent to the initial cylinder, and we will see that the cylindrical surface grows in diameter, which is not realistic. Now let's move on to the next support, the compression-only support. This support can be thought of as frictionless contact with a rigid object not modeled. The body is free to slide in tangential direction, free to lift off in negative normal direction, but cannot move in the positive normal direction. This support is useful to model a rigid pin in a hole in large deflection analysis or something resting on a stiffer part. A point to note here is that this is a nonlinear support, so it takes extra computations. After the compression-only support, let us talk about the elastic support. This support is useful to model the parts that are not rigid, but you can define a stiffness in the direction normal to the surface, such as a structure connected to a ground or foundation. When this support is applied to a surface, then the surface is free to slide in the tangential direction. A practical example where this support can be used is a building's foundation. The foundation of the building rests on soil, and the stiffness of the soil may be represented by an elastic support, although the tangential stiffness is neglected. We don't want to model all of the soil, but its stiffness may be important since it may not be rigid compared with the building materials. Next, let us discuss the remote displacement support. Consider a rigid object bounded to the part's surface, but its motion can be controlled at a specific location. Using the remote displacement support, we can transfer this displacement or rotation from rigid body to our parts of interest without modeling the rigid part. This is useful, for example, if you want to apply a rotation from a location in space to a surface. For example, here we have a part connected to the hinge, and the part can rotate about that hinge. However, the hinge is not part of the model. In this case, we can apply a remote displacement to represent the effect of the hinge part. The center of the remote displacement should correspond to the center of the hinge, and we can then apply rotation to rotate the part without modeling the hinge. Now we know that supports help to truncate the domain, but where we are truncating the domain is also important. We should always think about the meaning of the support we want to apply and consider if the situation is appropriate. If the boundary condition is not rigid, think about whether the rigid condition will lead to conservative or unconservative results. If needed, you may want to model the additional flexible parts and connect the parts via contact. Also, Savinian principle says that difference between the effect of two statistically equivalent loads becomes smaller at larger distance. The same can be said for boundary conditions. After truncating our domain by applying the relevant supports, we solve the model. We can drag and drop the support boundary conditions on the solution branch to obtain the reaction force at that support. This will help us to check the balance between the applied and reaction forces. But we should be careful while evaluating the support's reaction forces. When the support shares vertices or edges with another support, then the sum of the reaction forces may not be balanced. This can be explained by the fact that the shared edges only have one set of nodes, even though it is common to two or more supports. In such cases, the reported reaction force on nodes of the common edge will appear in reaction forces for both the ports. Thus, if we need to obtain accurate reaction force for each support, we should ensure that supports do not share edges or vertices with other items. Now, let's use a simple demo to illustrate the effect of supports in a simulation. Here, we have a cylindrical geometry sitting on a recessed base. sliding is allowed between the surfaces of the cylindrical part and the base part. You can see that the cylinder can rotate along the axis and can be lifted from the base. To simulate such a situation, we can use frictionless contact between the two parts. On the top surface of the cylinder, a force is applied to a section of the area in the negative y direction. For materials in this model, the base is made of steel and the cylinder is made of aluminum. Because of this, we know that the base is much stiffer than the cylinder. Now, in this model, we'll use an appropriate boundary conditions to replace the base, so that we don't need to worry about frictionless contact, and doing so simplifies the calculations. First of all, we notice that the behavior of the model is expected to be symmetric about this plane. So we just need to have half of the geometry. And also, the base can be removed as we will use a boundary condition to replace it. Now, let's go to Ansys Workbench. We can drag a static structural analysis from Toolbox. The geometry file is prepared, so we can just right mouse click on Geometry, Import Geometry, then select the geometry file for this problem. Now, we can just double click on Model to open Ansys Mechanical. First of all, let's check the unit system. Here we're using millimeter and kilogram unit system. For the material, we assign aluminum for the part. Next, let's define the symmetry region of this half cylinder. We can right mouse click on Model from Tree Outline and insert Symmetry. Then right mouse click on Symmetry, insert Symmetry Region. Here we select all exposed surfaces on the symmetry plane and also make sure that the symmetry normal is the x-axis. For the mesh, we apply a sizing control on the part and set the size to be 10 millimeters. Generate the mesh to visualize the elements. Now we can apply the load to the cylinder. Let's right mouse click on Static Structure on the tree outline, then insert a force. Let's scope the small area on the top surface of the cylinder. We can switch the mesh view on and off by clicking on Show Mesh. The force is defined by component and the value is 50,000 Newton in the negative y direction. Now about the boundary conditions. Since sliding is allowed between the base and the cylinder, it definitely shouldn't be a fixed boundary condition used here. As we mentioned before, if the base is modeled, frictionless contact should be defined between the two parts. So off the top of our head, frictionless support could be a good option here as a boundary condition. Let's have a try. We can right mouse click on Static Structure on the tree outline and insert a frictionless support. We can see from the geometry that the outer surface of the half cylinder is already sliced to have an area corresponding to the area in contact with the base. So for the frictionless support, we should scope both this area and the bottom surface. The model is ready to solve. Since everything is linear, this model solves really fast. Let's insert total deformation and equivalent stress results under solution and evaluate the results. Here, we can go to the Results tab and go to Edges, turn on Show Undeformed Wireframe to have a better idea of how the model deforms. Note that the deformation is exaggerated to visualize the deformation easily. If we change the scale to be 1, we can see that the real deformation is fairly small. So the question is, does this result reflect reality? Intuitively, if we have an eccentric load on a cylinder, we expected that the opposite side would lift. Of course, we're solving a small deformation problem here, and it's normal that the deformation might not be clearly visible. But if we probe results on the bottom surface, we can see that the results are almost zero. Also, since the cylinder is allowed to lift up, the stress on the bottom surface can be compressive or zero, but it definitely cannot be tensile because nothing should be preventing the bottom of the cylindrical part from lifting off. To check this, we can insert a normal stress result over the bottom surface of the cylinder. We can right mouse click on Solution, Insert Stress, choose Normal Stress, Then scope the bottom surface and set the direction to be Y. From the color scale, we can see the range of the normal stress in Y direction goes from negative values to positive values. In this case, a negative value indicates compression in the Y direction, and a positive value indicates tensile. If we probe values on the surface, we can see that near the loading area, the stress is compressive and gradually it becomes tensile if we leave the area directly under force. Apparently, this does not reflect reality, as the material on the bottom should not be in tension for this problem. We should recall that although frictionless support allows the surface to slide freely, it does not allow movement in the normal direction, including separation between the part and the ground. Therefore, frictionless support is not the right boundary condition to use for this problem. This makes us realize that we should have a boundary condition that allows not only for free sliding, but also separation. Luckily, we do have such an option, which is the compression-only support. As indicated by the name, only compression is constrained by this support, with no resistance for separating or sliding. Now, let's go back to the workbench schematic, copy the model we just worked on, and open the copied model in Mechanical. Let's suppress the frictionless support first. Then, we can right mouse click on Static Structure on the tree outline and insert a compression-only support. We scope this to the sliced bottom area on the cylinder surface and the bottom surface. Solve the problem again. This time, you will notice that the model takes more time to solve. And if you click on Solution Information and set the solution output to be Force Convergence, you will notice that the solver is trying to solve the problem iteratively. Why is this? This is because compression-only support is a nonlinear support, since we don't know beforehand what portion of the supported surface may separate or lift off. For nonlinear analysis, an iterative solution is needed. Now the problem is solved successfully. Let's have a look at the results. First of all, for deformation, you can see that at the bottom, the area far from the force actually has some deformation value. If we scale the deformation, now we can see clearly that the cylinder is lifting up on the opposite side, which is expected. Also, for the normal stress in the Y direction on the bottom surface, if we probe the results for the area far from the force, the values are almost zero, indicating that for these areas, the support is not providing any tensile or compressive force. Here is the side-by-side comparison of total deformation and equivalent stress from the two models with different boundary conditions. Same legend scales are used. It's quite obvious that the results are different. In conclusion, we can see that for this problem, frictionless support is not the right boundary condition to use and leads to incorrect simulation, while compression-only support provides a more realistic simulation of the boundary condition. Let's summarize the key takeaways from this video. Supports are used to represent components that are not a part of the numerical solution, but are interacting with the mesh. Using the appropriate support is essential for two reasons. First, choosing the right support helps assure that the simulation model will properly represent the boundary condition. Using wrong boundary conditions can entirely change the nature of the problem, thereby significantly skewing the results. Secondly, selecting the proper support can help to truncate the model. Truncating the model can represent the right approximations of interacting bodies and the working environment without actually modeling them. This can reduce computational effort while still obtaining numerical accurate results. Also, the reaction forces are summed when reporting the total reaction force for each support. However, if there is a common edge shared between two supports, be careful, as the reaction forces of the nodes on the common edge will appear in the total reaction force for each support. I hope you have found this video useful. Thanks for watching, and don't forget to visit courses.ansys.com to discover more useful courses.